This is the second of perhaps 3 or 4 videos on section 5.1 and 5.2 about linearization and nullclines, are sort of the main topics where we're trying to come up with methods for trying to understand nonlinear systems without a computer. But as I mentioned in the last video, the most important thing, of course, are my long and lame jokes. These jokes are not, by the way, meant to have anything to do with math. They're just kind of jokes from my childhood that I learned from my cousin named Jeff Kinney and his other cousin named Jay Morey. They were the ones who told me about these jokes, and you can blame them for how bad they are, but I kind of enjoy them. So the last one was Martian Baseball, Almighty Casey Almost Saved the Earth. Today you've got Don't Touch Me, The Mystery of the Purple Gorilla, and for the next video it's The Kid Who Couldn't Stop saying strawberries. And these jokes do get lamer and lamer as we go along. So if you just can't stand it, you can turn it off when we get to the joke. But what was the math we did in the last video? We were trying to understand a nonlinear system right here. dx dt is xy minus 4x, and dy dt is y minus x squared. And we're trying to draw the phase plane of this without using technology. Is such a thing possible? Yes, you can use your head. You can use ideas to not draw perfect representations of the phase plane, but good enough to get the qualitative picture of the nature of the solutions. As always, the first thing to do with these things is to try to find, if you can, the equilibrium points. We found 3 equilibrium points. These 3 points, -2, 4, the origin 0, 0, and 2, 4. As I mentioned in the previous video, the origin is definitely not always an equilibrium point, though it seems to always be. There are definitely plenty of systems where it's not, though. Notice you got more than one. That can happen for nonlinear systems. For linear systems, the dichotomy was either it's going to be one equilibrium solution or infinitely many. Here we have 3. Okay, you can have no equilibria, like if x prime was 1 and y prime was 1, that would be no equilibria. You can have 1, 2, 3, infinitely many. There are infinitely many possibilities for nonlinear systems. And here's what the phase plane looked like. Remember this picture? You should be watching this video hopefully shortly after you watch the first one. I'm really, again, combining the ideas of section 5.1 and 5.2 in all of these videos together. And so the first thing we did was actually an idea from section 5.2. We looked at what are called the x and y nullclines. X nullcline in blue was this horizontal line and also the vertical y-axis, where x is 0. Y nullcline is y equals x squared, this parabola in red. The x nullcline is where the vector field is vertical, and the y nullcline is where the vector field is horizontal. Where those two kinds of nullclines cross, you get your equilibrium points, 3 of them, here, here, and here. And in between, you think about what the signs of dx dt and dy dt are to determine whether solution curves are going to move northwest, like they are here, or northeast, like they are here, or southeast, like they are here, or southwest, like they are over here. We drew in the equilibria, and by using the technique called linearization, which is the main focus of section 5.1, we tried to figure out what the phase portrait looked like near these equilibrium points. And what did we find? Well, when you're looking near the origin, the nonlinear terms can be ignored. So we can throw away the x times y here and throw away the x squared, and just essentially think of the system as having a -4x and a y on the right-hand side. The associated linearization, or linearized system, for this nonlinear system at this point, 0, 0, is this linear system down here. Now, this linear system has an equilibrium point at the origin for it. And it's got a phase portrait that looks like this. It's a saddle point at the origin. Its eigenvalues are 1 negative and 1 positive. That's what it looks like near the origin for this linear system. The nonlinear system also looks like this, but only near the origin. For the linear system, it's this way, this kind of pattern for the entire plane. For the nonlinear system, it looks like this, but only in a neighborhood near the origin. So I kind of drew in a little dashed circle near the origin and said, you can use your imagination a little bit to realize that you've got essentially the picture I had in the previous slide in this little circle. You've got essentially, you definitely have solution curves moving away from the origin along the y-axis. Those are straight line solutions. And you've got some curved solutions that approach the origin tangent to the x-axis, so that when you get real close to the x-axis, they look like they're on top of the x-axis, even though they're really not. Those approach the origin as t goes to infinity. And in between, you've got these other solutions that kind of follow this one backwards in time and follow this one up forwards in time. And you can think about how they're going to cross these nullclines based on whether it's an x or y nullcline. We also looked at the linearization near this point. Now, to get the linearization near that point, you either have to do the trick of using a substitution like the book introduces at the beginning of section 5.1, or the quicker method. And I want you to know both methods. The quicker method, though, is to use something called the Jacobian matrix. The Jacobian matrix for a vector field is, if it's a two-dimensional vector field like this, it's a 2x2 matrix. And the entries are the partial derivatives of the components of the vector field. First component along the first row, partial derivative with respect to the first variable, and then the second variable. Second component of the vector field along the second row, it's partial with respect to the first variable, and then it's partial with respect to the second variable. Based on this particular example, this is how the partial derivatives turn out. You then plug in the equilibrium point in question, and you should be doing this only for equilibrium points. See what you get? The linearized system for the original nonlinear system is this. This is a linear system whose phase plane near the origin for this system looks like the phase plane near the point 2, 4 for the original nonlinear system. I'll say that again. For this linearized system of the nonlinear system at this point in question, at this equilibrium point, the phase plane, which turns out to be a spiral source based on the trace-determinant, turns out to look like, be qualitatively the same as the phase portraits for the original nonlinear system, not near the origin, but near this equilibrium point 2, 4. If you figured out what the phase portrait for this would look like, it would look like a spiral source that where the rotation is clockwise. And I mentioned that you can look at the nullclines here too and see that the rotation is clockwise. If you just look at the directions of these arrows, it's got to be a clockwise rotation around that point. And that allows you to draw in some solution curves like this one that would go around and around and move away from it. I also mentioned that one of these solution curves has to eventually approach the origin, but it is just one of them. If I follow this one kind of backwards in time, maybe it goes about like this. In the last video, I called that a separatrix, and you do read about separatrices in section 5.1. I guess technically speaking, by the definition of separatrix as being a solution curve which separates the phase plane into two distinct long-term behaviors, it actually is not, even though it kind of looks like one here. If your initial conditions are up here, for example, it seems like at first they certainly move away. up toward positive y values as t gets larger, whereas solutions that are down below this curve move down this way as t increases. Y becomes more and more negative. However, solution curves that start in here, say right here, are going to travel like this. They're going to cross the red curve horizontally before they go back up and cross this blue curve vertically. And they're moving this direction as t increases. They're moving now to the northeast. They are going to eventually cross y equals x squared again and be forced back downward and eventually have the same long-term behavior as t goes to infinity. That's what's going to happen. So the long-term behavior is going to be the same no matter which side of this one particular special solution you're on. Both as t goes to plus infinity and as t goes to minus infinity, you'll end up going back toward this point. X will approach, this was x equals 2 and y equals 4. X will approach 2 and y will approach 4 as t goes to minus infinity for any initial condition in this first or fourth quadrant of the regular plane. Now, I could continue going ahead and doing the linearization for this point by taking the Jacobian and plugging in this point. X is negative 2, y is positive 4. I won't go through that in detail. You could try it on your own. You will get a spiral source again, but actually this time the rotation is going to be counterclockwise. Now, you could check that by actually looking at the linearized system and seeing that its rotation is counterclockwise. But there's a neater way to check it here. Let's come back up to the screen here. The neater way to check this, and maybe this is something that has occurred to you already, is that this system actually has some symmetry to it. If you look at the phase plane here, it's symmetric with respect to the y-axis. The graphs of solutions to the left of the y-axis are going to be the mirror image of the graphs of solutions to the right of the y-axis. That definitely won't always happen. In fact, you might even say it usually does not happen, but in this case, it does. How could you check that algebraically? Well, basically the fact that in both right-hand sides, if you replace, in the lower one, if you replace x with negative x, so replace the x there with negative x, you really get the same right-hand side for the second equation because negative x quantity squared is the same as x squared. So dy dt doesn't change when you replace x with negative x. So at any point down in the phase plane, the vertical component of the velocity will always be the same as long as if you're looking at points that are symmetric with respect to the y-axis, meaning their y-coordinates are the same and their x-coordinates are opposites of each other. Like this point here, say, and this point about there. The vertical component of the velocity is going to be the same. Now you can see the vertical component of the velocity here is going to be positive because the solution curve is moving up. Same positive vertical component here. As far as the horizontal component of velocity, you'd have to go to the dx dt equation. If you replace x with negative x up there, the equation doesn't become the same. It becomes the opposite of itself. The right-hand side has the opposite sign as it originally did and the opposite value. So coming back down here, the horizontal component of velocity at a point right about here might be a positive number, like perhaps positive 1 or something, because there's a motion to the right. The horizontal component over here would have to be negative 1. So the solution curve and the velocity vector has to be the same y component but the opposite x component. And that is essentially what allows you to say that solutions over here are the mirror images of over here. So instead of clockwise rotation, you get counterclockwise rotation. Outward, it's still a source. This kind of thing. Down here you can see it's similar, it's a reflection. And once again, you're going to have one special solution that heads exactly toward the origin as t goes to infinity. It is a special solution. I guess, again, technically it's not a separatrix, but it is special. In fact, these two solutions are both part of what's called the stable manifold of the origin here. And I won't get into what that means in this video. Okay, so that's essentially what the phase portrait looks like, and we figured that all out without a computer. What I'd like to do now is I'd like to generalize this example and make it part of a one-parameter family of nonlinear systems by making a parameter in here. And we're going to, of course, then look for bifurcations. And you will need to do this sum on your homework. So the one-parameter family is going to look like this. The dt is going to be xy minus a times x. So a is going to be my parameter. In the example I just did, a was 4. And dy dt is going to be y minus x squared. Again, our first order of business is to think about equilibrium points by setting these right-hand sides equal to 0. Set that equal to 0, set this equal to 0, and solve the resulting system of algebraic equations. 0, 0 is still going to be an equilibrium point no matter what a is. On the other hand, if y is a, and think about this, if x is plus or minus square root of a, at least when a is greater than or equal to 0, you're going to have those producing equilibrium points as well. If a is greater than 0, you're going to have 3 equilibria. That tells you right away a bifurcation is going to occur at a equals 0. Again, it'll be plus or minus square root of a, comma a. That really is 2 equilibria, plus square root of a, comma a, and negative square root of a, comma a. And the origin. If a is equal to 0, you've got 1 equilibrium at the origin, and that's going to be true if a is less than 0 also. You've got 1 equilibrium if a is less than or equal to 0. And that'll be at the point 0, 0. Now, we could jump right ahead to drawing nullclines in both of these cases. In fact, the y nullcline is going to be the exact same as before, the parabola. The x nullcline is going to have the y-axis still as 1, no matter what a is, x equals 0. And a horizontal line at y equals a, that horizontal nullcline will change as a changes. As a gets bigger, that horizontal nullcline will go up, which should give you some immediate intuition about why we've got 3 equilibria in this case and 1 equilibrium in that case. But I want to jump right away to the Jacobian matrix. It's going to look pretty similar to the last one, except we have the a in there. We've got the derivative of the first component with respect to x to be y minus a. It was y minus 4 before. Then with respect to y, that'll still be an x. Now look at the second component. With respect to x, it's negative 2x. And with respect to y, it's 1. Let's figure out what the Jacobian is at these 2 equilibria when a is greater than 0. In a sense, when a equals 0, these 2 equilibria, you can see, coalesce into the origin. You might, I suppose, when a equals 0, you could think of the origin as somehow being an equilibrium point of multiplicity 3 or something like that, but we won't worry about that. What I'm writing here, we'll assume a is positive. This notation is emphasizing that I'm plugging that equilibrium point into the Jacobian matrix. Let's see, y is a, so y minus a is going to be 0. no matter what A is, the upper left entry of the Jacobian matrix is going to be 0. The upper right and lower left entries do depend on A. I'll write plus or minus square root of A for the upper right, meaning it would be plus square root of A if x is plus square root of A, and minus square root of A if x is minus square root of A. Since I have a negative sign there, I'm actually going to write minus plus in the lower left entry, minus plus 2 square root of A, to emphasize that the signs of these things are always opposite of each other. And the lower right entry is always going to be 1. The trace is always going to be 1 no matter what A is. And the determinant is going to be 0 minus plus or minus square root of A times minus plus 2 square root of A. From that product, you'll always get a minus sign, but because of the minus sign here, you ultimately always get a plus sign. You get plus 2A. Again, we're thinking about A being positive here when we think about this. So what is that telling us? In the trace-determinant plane, the parametric curve described by these equations as A increases away from 0 is going to be a curve whose trace is always 1. The first coordinate is always 1, and the second coordinate, the determinant, is always increasing, so it's a curve that moves upward like that. It's not a solution curve, it's just a keeping track of the tracing determinant as the parameter A changes. In particular, again, there's a bifurcation at A equals 0, where I guess, the tracing the determinant would be 0 there, if I were including that case here. And there's going to be a bifurcation at another value of A when we cross the repeated root parabola d equals t squared over 4. And if you think about that, that's going to happen when 2A equals 1 squared over 4, or 1/4. In other words, A is 1/8. Looks like that's another possible bifurcation value. It certainly is for the linear system if we're thinking of changes from non-spiral real sources to spiral sources as being bifurcations. And again, I mentioned before that some mathematicians don't think of that as a bifurcation. In fact, most mathematicians who do this don't think of that as a true bifurcation in what's called a topological sense. But for us it is. Changing from non-spirals to spirals, we think of as bifurcations. So it certainly is for the linear system. Is it for the nonlinear system? Is 1/8 a bifurcation value for the nonlinear system? Well, it's a little trickier. Basically, you have to trust the following facts, okay? Focusing on me. There's something called the Hartman-Grobman Theorem, which is essentially a higher dimensional generalization of the linearization theorem in section 1.6 in the book. That says if you've got a nonlinear system and you're looking at an equilibrium point, and you're looking at the associated linearized system for that equilibrium point, that the phase portrait of that linearized system will match the phase portrait of the nonlinear system near the equilibrium point. They'll be qualitatively the same, at least again if you focus just in a neighborhood of that equilibrium point for the nonlinear system. That'll be the case if the eigenvalues of the linear system all do not have a real part equal to 0. Now you can think of real numbers as being complex numbers if you like. Real numbers are just complex numbers with an imaginary part equal to 0. And so to say the real part of your eigenvalues can't be 0 includes the case where the eigenvalue itself can't be 0, the number 0. So as long as the real parts of all the eigenvalues, and for two-dimensional systems we only have 2 of them, and if they were complex they'd be complex conjugates, as long as those real parts, or the eigenvalues themselves if they're real, are not 0, then the qualitative nature of the linearized system will match the qualitative nature of the nonlinear system near that equilibrium point. Those are called hyperbolic equilibrium points when that happens. Now, what about the non-hyperbolic ones when the real part is 0? Well, basically, anything can happen, and it depends on the situation. There's also something, a word of warning here. The Hartman-Grobman Theorem, as it's traditionally stated, only, like for sources, thinks of spiral sources and non-spiral sources as essentially being the same. They're both sources. But because we know the vector field is not going to change very much as the parameter changes, you really can still say it for spiral versus non-spiral too. So ultimately, just like we saw when A was 4, that we got spiral sources, when A is between 0 and 1/8, the fact that the linearized system has non-spiral sources for these 2 points will be enough to say that the nonlinear phase plane will have non-spiral sources there too. Could we draw it? Well, we could try it. It's a bit tricky. I'll see if I can draw it real quickly here, and then we'll get on to our joke. Well, it's going to be a little bit of the computer too, but I guess I'll have to save the computer for the third video since the joke's the priority. Where are my priorities? I know this is getting long as it is anyway. So let's see if we can at least believe with a picture perhaps that we're going to get a non-spiral sources when A is between 0 and 1/8. When A is between 0 and 1/8, we're going to have our x nullcline be pretty close to the x-axis. It's just barely going to be above it. And your equilibria are all going to be pretty close together. This one's still going to be a saddle point, I think. Maybe I should check that. Yeah, it'll still be a saddle point. Looking like this. I drew that along the x-axis, but it's technically not. I guess I'm kind of believing it just already and looking at this. You've got to cross this horizontal and this vertical. Some solutions are going to go like this, but this one, it's going to seem like it won't really have, if you follow this one backward in time toward this equilibrium point, it's going to kind of seem like it doesn't have enough time to spiral, in a sense. I mean, this is definitely no proof, but it's going to seem like to me, like it's probably going to go ahead toward that equilibrium point as t goes to -infinity without spiraling. Now, I might be wrong about that, but it seems reasonable, at least. And that's all I'm trying to see, is if this seems reasonable. Probably you'll have a solution that'll go off this way. You can find the eigenvectors, too, for the linearized system, by the way, and see if you have one line of eigenvectors that seems parallel to about this direction that I'm showing right here. This will be a source. I'm guessing, well, this is a little tricky. Maybe there's another line of eigenvectors for the linearized system that's going to go up this way. It can't point the other way because the directions of the vector field is going to be northeast in this region. So I'm a little unsure about this. A lot of this is done with some hesitancy. And you should probably check it with HPG System Solver, which is what I wanted to do with my computer here anyway, but I've run out of time. So, go ahead and try that. Take a HPG System Solver, plug in this system, say with A equal to 1/16. Should be what, like 0.0625, I think? Try that for the A and see if it does seem like it's non-spiral. All right, on to the joke. The mystery, don't touch me, the mystery of the purple gorilla. There's this guy who's a traveler, and he's wandering around the country, and he wants to stop for the night. It's raining, it's cold. Comes to this farmhouse and asks the farmer, "Can I please stay in your house for the night?" And the farmer doesn't feel like letting him in the house, a stranger. But he says, "Well, you can come out to this haystack here, and you can sleep by this haystack. There's a little bit of shelter from some of the straw. It gets over your head. You can dig into the haystack a little bit if you want. But wait a minute, I am a little concerned about you. I've got to show you something that you really need to take heed of." So the farmer reaches into the haystack, and there's a doorknob in there. And the farmer turns open the door, and there's a long passageway into the haystack somehow. And the farmer says, "Come with me, I need to show you something." And so they walk down the long passageway, through more doors and through more long passageways. And they're about to open one final door. And the farmer says, "I'm going to show you here must be kept secret. And you must obey me here." So they open up the door, and inside they see this cage. And inside this cage is this humongous, gigantic purple gorilla. Purple gorilla's asleep. Well, the farmer whispers to the man. He says, "No matter what you do not touch this purple gorilla." And farmer makes the guy promise, and so he promises, and they go back out. And the farmer says, "Well, good night. Now remember, do not touch that purple gorilla." So the guy tries to get to sleep, but of course he just can't. He's wondering what's going to happen if I go touch that purple gorilla. So he goes back in through all the corridors and through all the doorways, and finally he gets to the purple gorilla, and the purple gorilla's sleeping so peacefully. Surely he can touch him without waking up. And he reaches into the bars and barely touches the purple gorilla. All of a sudden, the purple gorilla wakes up with a gigantic roar and sees the man, and just really gets angry and grabs the bars and starts pulling them apart. And of course, the guy's just scared out of his wits. He starts running out the doors and through the corridors and out the haystack and running for his life. And the purple gorilla pulls the bars apart, starts rampaging down through the corridor and out through the haystack, and starts chasing after the guy. The purple gorilla is really fast, but this guy does happen to be a long-distance runner. And he runs fast, and for quite a long time, the purple gorilla still hasn't caught up to him, but he's right on his tail. Now, he happens to come across a bicycle, and he picks the bicycle up, jumps on it, because he's been pretty tired from running, but he's got enough energy to ride the bike pretty hard, so he's riding the bike pretty hard across the country. The purple gorilla is right on his tail, but he's still staying ahead of him. He's getting pretty exhausted, but he comes to the ocean. He feels like he's out of room. He has nothing left to do but jump into the ocean and start swimming. Hopefully the purple gorilla can't swim. He happened to be a long-distance bicyclist too. I guess he's a triathlete. He also happens to be a long-distance swimmer. He starts swimming across the ocean. The purple gorilla, unfortunately, jumps in after him, and the purple gorilla is a very good swimmer too. He's right on his tail. Miles and miles of swimming go on. The purple gorilla is right on his tail, just screaming. Rawr! And the guy's still just so scared. The adrenaline's rushing. Finally, he comes to this seemingly deserted island, and he runs up a hill, and he's out of breath. He just can't keep going. He's about to give in and let the purple gorilla do whatever. The purple gorilla is coming up the beach, running after him. And he's about to give in to his doom. All of a sudden, the purple gorilla stops, looks around, goes into the forest. The guy wonders, should I try to escape? But he doesn't have the energy to escape anymore. He waits around. All of a sudden, some animals come out of the forest, and the purple gorilla comes out. And they all start coming toward him slowly. And the guy wonders, I guess they all want to eat me, or what, do they want to be witnesses to my doom? And the purple gorilla's coming up, really angry. And the guy cowers. And the purple gorilla comes up to him and raises his arm and lightly touches him and says, "You're it."